Hi, myself ELDHO Edison. I would like to present the review of the paper titled A Phosphorene Graphene Hybrid Material as a High Capacity Anode for Sodium-Ion Batteries, published in Nature Nanotechnologies 2015. This is a brief outline of my presentation. Introduction, the fabrication of the phosphorene graphene hybrids, the sodiation mechanism in the hybridizer, and the electrochemical test results, and a brief summary. Introduction. Currently, lithium-ion batteries are widely used in portable electronic devices such as mobile phones, laptops, etc. due to their high energy density. However, recently sodium-ion batteries have attracted great interest as an alternative to lithium-ion batteries due to the cheap and abundant sodium reserves as well as its similarity to the lithium-ion battery chemistry. The figure shows the components of a sodium-ion battery. Consists of a cathode and an anode separated by a separator and filled with an electrolyte, which is a sodium salt dispersed in a solvent. During the charging of the battery, the sodium ions travel from the cathode to the anode through the separator and they intercalate into the anode. During the charging process, energy is stored in the battery. During the discharging process, when we need to supply energy to an external load, the sodium ions de-intercalate from the anode and move back to the cathode, and the electrons will move through the external circuit delivering current to the load. This is the operation during the charging and discharging of the battery. And conventionally for lithium-ion batteries, the anode is graphite. However, it is not suitable for sodium-ion batteries, mainly because of the larger size of sodium-ion, which is 2.04 angstroms compared to 1.52 angstroms of lithium-ion. And in this paper, the authors have introduced a novel phosphorene graphene hybrid anode for the sodium-ion battery, and this anode offers very high capacity and good cycling performance. The authors also propose the sodiation mechanism in the anode, and they make use of transmission electron microscopy and XRD techniques. The reason for choosing phosphorus for the active anode material is that it reacts electrochemically with sodium to form the Na3P phase at a low potential, and it offers a high capacity of nearly 2600 milliampere hours per gram. Coming to the fabrication of the phosphorene graphene hybrids. Initially, the phosphorene and graphene were synthesized separately using a solution-based exfoliation technique. And the evidence of the few layer phosphorene and graphene were obtained through transmission electron microscopy and atomic force microscopy imaging techniques. In order to synthesize the phosphorene graphene hybrids, they made use of self-assembly of the phosphorene and graphene in N-methyl 2-pyrrolidone dispersions. And the sandwich structure with alternate layers of phosphorene and graphene was imaged and analyzed through transmission electron microscopy and energy dispersive X-ray spectroscopy techniques. So the figure shows the evidence of the monolayer and few layer phosphorene. You can see single layer phosphorene and two layer phosphorene. So the figure B shows the transmission electron microscopy image of the tri-layer phosphorene nanobelt, and the long edge is shown in the inset high resolution transmission electron microscopy, indicating the lattice spacing of 7.7 angstroms. The green square marked here is shown here in figure C as a high resolution transmission electroscopy image with a lattice spacing of 4.4 angstroms. Figure D shows the schematic of the square phosphorene with bond lengths labeled 2.224 angstroms and 2.2 to 44 angstroms with a high reactivity plane indicated, which is along the bond length, along the higher bond length. Figure E shows the atomic force microscopy image of the phosphorine layers, and the thickness of each layer marked 1, 1 prime, 2, 2 prime is shown in figure F. For example, the thickness of the 1, 1 prime is shown as 1.57 nanometers in figure F, and correspondingly we have the thickness of the different layers. So G shows the XRD pattern of the bulk phosphorus and the phosphorine layers, and the figure H shows the enlarged amplification of the XRD pattern of black phosphorus and phosphorine at low angles, 8 to 20 degrees. The digital photographs of the NMP dispersions are shown in figure A, and the TEM image of the phosphorine graphene hybrid, with which we can see the alternate layers of graphene and phosphorine in figure C. So the phosphorine layer will be sandwiched between two graphene layers. So the Raman spectra and the XPS analysis is also shown in figures D and E respectively. So the authors have proposed the sodiation mechanism in the hybrid structure, and they have validated the same using in situ transmission electron microscopy and ex situ XRD techniques. And they propose a two-step sodiation mechanism, where the first step is the intercalation of the sodium ions into the structure, and the second step is the alloying reaction of sodium with phosphorus. And this is schematically shown in figure A, where we have the black phosphorus layers, phosphorine layers, and we can see that the high reactivity plane is along the x-axis. So the authors propose intercalation of the sodium ions along the x-axis, as seen here, intercalation along the x-axis, and this is shown in the time-lapse image of time-lapse in situ transmission electron microscopy image, where we can see that the intercalation of the sodium ions along the x-axis causes a volume expansion along the y-axis. So the first step is intercalation, and the next step is alloying. So the sodium ions, they alloy with the phosphorus to form the Na3P phase, thereby providing a very high capacity of around 2600 milliampere hours per gram. And the role of graphene is to buffer this anisotropic volume expansion along the y and z direction, and thereby it prevents the disintegration of the structure and gives it very high cycling stability. So as seen in the TEM images, the channel width along the x-axis is greater than that of the y-axis. Therefore, the sodium ion diffusion is along the x-axis, causing volumetric expansion along the y and z directions. And the graphene layers, they buffer the anisotropic volume expansion, and also graphene is highly conductive, so they also act as an electrical highway. The sodiation behavior was also evidenced using the ex situ XRD techniques, where we can see that there is a shifting of the two characteristic peaks, 002 and 004 peaks, to the lower angle as shown in figures B and C. This indicates that there is an expansion, there is a lattice expansion happening due to the intercalation of the sodium ions. We can also see the alloying reaction by the formation of the Na3P phase at a lower voltage of 0.1 volts. Thus, the sodiation mechanism is supported by the evidence from in situ TEM and ex situ XRD. So the authors have performed electrochemical tests using this hybrid structure, and they found that the carbon phosphorus mole ratio in the structure affects the performance significantly, and they have optimized a ratio of 2.78:1 of carbon is to phosphorus, which has 48.3% of phosphorus by mass, and it was found to be optimum in terms of capacity as well as cycling stability. And graphene was found to be inactive towards the sodium storage. However, it acted as a good buffer in order to contain the volume expansion and thereby maintain the integrity of the structure. And the electrochemical tests were carried out in a 2-electrode arrangement in the voltage range of 1.5 to 0.02 volts at a rate of 50 milliamperes per gram. So the figure shows the cycling performance of the phosphorine graphene hybrids. At the ratio for the ratio of 1.39:1, you can see that the capacity fades rapidly, and it's much below the theoretical capacity when it reaches 100 cycles. Whereas for the optimized ratio of 2.78:1, you can see that the capacity is maintained for even up to 100 cycles. The fading is very less. The figure B shows the galvanostatic charge discharge curves of the phosphorine graphene hybrid of the optimized ratio. You can see the first discharge shown here, and the second and 50th discharge corresponding to the same, follows the same path, indicating the reversibility of the sodiation and desodiation. Figure C shows the charge discharge performance at different current densities, like starting with 50 milliamperes all the way to 26 amperes per gram. And the cycling performance at different C rates, where one C rate corresponds to the discharging of the battery in 1 hour. The others have performed the cycling tests for different C rates. So at low C rate it has very high capacity, and at increasing C rates the capacity was found to be less, but still it was found to be stable. So to summarize, the paper presents an in-depth study of the novel phosphorine graphene hybrid anode for sodium-ion batteries. They discuss the synthesis of the hybrid structure and propose the mechanism and experimentally validate the same using advanced characterization techniques. And the role of both phosphorine and graphene in the sodiation process are explained clearly. And the electrochemical performance studies, they demonstrate the high capacity and good rate performance of the proposed hybrid structure and its potential as a new anode material for sodium-ion batteries. Thank you.